Okay, so another example of rearranged equation. I put this in just because I thought I'd tell you a little bit about it. What we're going to do is we're going to work out how high it is possible to pole vault. Okay, so a couple of years ago, the pole vault world record was recently set by this guy, Raymond or Renaud Levine, up here, 6 meters 21, I think, something like that. Okay, women's world record is here, and my personal best is here at 4 meters 32. So I would have had the world record in 1920, but I'm not that old. Anyway, so one question you can ask is, can this carry on increasing forever, or is there some limit to how the world record will proceed? Okay, so how high can a human vault? Oh, I put these in. Oh, right in the face. Some quite good ones here. This one's particularly amusing. Bit of that, and it's really hilarious. And this one is the most painful. All looking really good, and then Anyway, you'll remember this. So here's our model that we're going to basically create mathematically to work out how high it's possible to pole vault. So our pole vaulter runs in as fast as they can. So they have some kinetic energy. Okay. So their kinetic energy can be described as 1/2 times their mass times their velocity squared, half mv squared. You might remember that from physics. Okay, they jump. Okay, so there's some energy in their jump, which we'll ignore, and then they convert all of this energy into height. Okay, so the amount of energy that they have at the top of their pole vault is essentially just their gravitational potential energy. Okay, so the kinetic energy can be described as 1/2 mv squared. Okay, and when they get to the top of their pole vaultness, their energy is the mass times gravity times height. Okay, you might have done this before at school. Potential energy is mgh. Okay, so our model is going to just basically, all it's going to do is say that you convert all of your kinetic energy into potential energy. So the whole system, kinetic energy equals potential energy, which is this equation here. Okay, 1/2 mv squared equals mgh. Okay, that is the model for as high as anybody can pole vault. Okay, so all we need to do now is rearrange that equation. Okay, so very simply, all we're going to do is we want to make h the subject of that equation. Okay, so we could divide both sides of the equations by mass and gravity. Bring those over to this side here. Okay, and then the mass then cancels out. So we've got mass divided by mass. It doesn't matter how heavy you are, it doesn't determine how high you can pole vault, which is good. Okay, so we end up with an equation like this. And then we can plug some numbers into that. So we know what gravity is. That's 9.81 meters per second squared. Okay, which you will remember from the first tutorial, I think, maybe? Maybe not. Yeah, you did that in the first tutorial, right? It's like question 14 or 13. Which is definitely in there, yeah? And V, our man here, Usain, okay, so he can run, when he gets like his fastest, when he was running the 200 meters, 44.72 kilometers an hour, which is pretty fast, okay? So all we need to do now is plug those equations into numbers. Plug those numbers into that equation, okay? But bear in mind that what we should always do is we should always convert stuff into standard units, or at least the units that we're interested in getting our answer in. So convert velocity into meters per second, into meters per second. So we need to times it by 1,000 to get kilometers into meters, and then divide by the number of seconds there are in an hour, which is 3,600. Okay? So our Usain here can run at 12.42 meters per second, which is still pretty fast. So we can then plug those numbers into the height. Okay? And you can do that in your own time. And notice that I'm now quoting the answer, okay, to the lowest number of significant figures that I was given information, okay, which in this case was gravity. Okay, so 7.86 meters. So 7.86 meters is the highest increase in potential energy that you get while pole vaulting. Okay? But you don't start off at the ground because your centre of mass is not on the ground while you're running, so a bit of height there. So it turns out that Usain Bolt, if he decided to take up pole vaulting, would be able to pole vault approximately 9 metres high. Okay? So that's what the model suggests. When we compare that to the actual world record, which is 6.2 metres, that's a lot more. Okay? So we can then go back, do that kind of like that scientific method that we did in the first couple of lectures. We go back and say, look at our model, and say, is our model realistic? Okay? So there are a whole bunch of reasons why our model might not be realistic in this case. So the speed that Usain Bolt runs, holding an enormous pole, is probably not as fast as he can run when he's not holding it, so his velocity is probably a bit less. And also maybe some of this energy transformation from kinetic energy to potential energy, maybe that's not 100% efficient. So we might go back and revise our model, okay, with some different data and some different assumptions. Anyway, so